We're up in the 14th floor in the main substation room, and what we have here is a series of double-ended substations. I'm going to walk you through what's typical of one of 4 units. They're pretty much all identical, but this will give you a feel for the basic components of this unit substation. Again, from a safety standpoint, we don't want to do any of this from an energized standpoint. We want to de-energize the equipment, not just when we're doing maintenance, but also when we're doing any kind of testing and inspection. And we'll go through each part of the substation one at a time. As we talked about from down below, you have a feeder that's coming up from the main incoming Pico service and is landing in this area here. So we're stepping the equipment down from 13,200 volts down to a usable 277 480 volts. So this is the main switch that's coming up from the one side of the unit substation. This is the local means of disconnect for the substation. This is the on-off lever, quick make, quick break. This is what we call a metal enclosed load break switch. This is not metal clad equipment like we were talking about downstairs. So this does not have the various barriers in between the different sections. It's basically medium voltage equipment inside a box. So if I opened up the front of this and I opened up the back of it, you'd be able to see right through because this is metal enclosed, not metal clad equipment. This particular switch is a fused switch. So downstairs we had the mains, which were providing short circuit and overload protection for that gear down here. What we now have is the main power comes up here. We go through a disconnect switch here, which has a set of fuses, which is designed to protect the transformer, which is the next step down. So what happens is we've got 13,200 volts, and it's going to be stepped down through the transformer down to 277 480. This is a very basic piece of equipment. It's sort of like a medium voltage safety switch, probably the best way to describe it. I've got cable connections in the back, and then I've got a quick make, quick break switch here to operate and open it. To operate the switch, there's a little safety bypass that has to be pulled out before you can change the position of the switch. It is quick make, quick break. We're not going to go into the details of the operation because, again, this is something that should be done by a qualified medium voltage electrician. From a service standpoint, this is even a simpler piece of equipment than what we talked about before. It's basically just got switches and fuses. So if you do experience some sort of interruption of power, you could potentially have a fuse blown out up here. So, after you de-energize the equipment, there's an interlock that prevents you from opening the door while it's in an energized position. So then you would check to make sure that the fuses are good or bad. From a cable connection standpoint, like we talked about downstairs, there are a set of infrared sights here so that you can go in and look at the switch here in the front, and then also I think we're going to see there's a set of IR ports in the back. Again, very basic operations. It's just an on-off device with a set of fuses whose primary function is to protect the transformer. From a service and maintenance standpoint, keep it clean, use vacuuming, and exercise the equipment annually if you have the opportunity. Every other year, you can probably stretch that out too. The nice thing about this is you'll get positive viewing through the window if the blades are in the open or disconnect position. So, another nice double check. Hey, the switch tells me it's open. Can I visibly see the blades? That would be the two-step process for safety, just to make sure before you open up the door. Any questions on the load interrupter switch? This is pretty basic. Come in the back, goes over to the front. It is a cable connection.
13.2 here?
It is 13.2 to here, and it is 13.2, sort of in the middle here. Okay, so what we have is a cable connection here from the bottom of the fuses all the way over to the connection to the transformer. And that's what this IR port is here, so that I can check to see is that cable connection to the transformer also a good connection, just like the cable connection in the back of the equipment.
That line VT that you saw on the floor that stepped you down to 120, that was just to feed the
The main equipment.
The main
temp.
equipment.
Yep, yep. Has nothing to do with the equipment up here. The nice thing about this, and that's a great question, is because this is just a switch, there really is no control power requirement. I mean, you're either going to throw it on and boom, you got 13.2, or you're going to turn it off and boom, you don't have 13.2, or the fuses are going to blow and boom, you don't have 13.2. Those are really your only three choices. But to your point, and that's a great question, you do not have to worry about any kind of control power whatsoever to make this switch operate. It's strictly a manual operating device. Great question. Okay, we're going to move down a little bit to the next piece of equipment, which is the dry type transformer. This is a dry vacuum pressure impregnated transformer. So it's not liquid. You don't need to worry about any fluid containment or anything like that. It basically is taking the 13,200 volts and stepping it down to 277,480, which is what you're going to use to distribute electricity throughout the rest of the building. You will have other transformers that'll step it down to 122.08, but the majority of your service is going to be 277,480. This particular transformer is what we call, it's got an ambient, and then it's also got a forced air rating. So that's what this compartment is here. This is a transformer temperature monitor, but it also has the ability to kick in fans. So this transformer has a rating of 1500 kVA, but then it can also go up to 1995 or 26.6 kVA with the fans on. So we're not really changing the transformer itself. The transformer is the transformer, but when we force air through it as opposed to just normal ambient air convection, we can get more power out of the transformer because we make it run cooler because we're putting fans on it. So that's the reason here. This is your transformer temperature monitor. You'll notice that it has thermocouples on the A coil, the B coil, and the C coil, and it automatically steps through and tells you what the temperature is on the coil. So for example, here the left one is 50 degrees C, the center is 52, and the right is 53, and it's a max of 68. Well, this particular unit is rated up to 150 degrees C. So your transformer is running pretty cool. Okay, so even at its peak, it was only at 68. So again, kind of going through the maintenance and looking out for the equipment, things like that. It might not be a bad idea when you're kind of making your rounds and looking around. Just make sure that you're not seeing any abnormal spikes on the transformer temperature. I mean, again, you can see it automatically cycles through. So if you just stand here for a couple of minutes, or actually probably 1 minute, you'll be able to see, okay, left, center, right, maximum. And if all those numbers are below 150, this transformer is doing well. It hasn't been stressed. The coils are being distributed equally. You're not getting any hot spots on the left or hot spots on the right. One thing I will say is once the building gets a little bit more occupied and you start pulling more effective amps, it's not unusual for the B coil to run a little hotter than the A and the C. And the reason is because the B is in the middle and it's got half of its coil blocked by one coil and the other one blocked by the other coil, where the A and the C, they have free air around them. So it is not unusual for the B coil to be slightly higher than the A and the C. That's nothing unusual. This, of all the equipment we're going to talk about today, this is the most important one to keep clean. Okay, this is the one, if you're kind of in that, oh gee, I can only work on, I have to go to an every other year, type of maintenance cycle instead of every year. This is the one piece of equipment you want to try to keep on the annual cycle. And the reason is, if you get particulate matter on the coils, and that particulate matter is conductive, okay, like cement dust. Okay, that's the worst offender, okay? And that's something we all see on job sites, is cement dust, okay? You want to keep that off of the coils. So One thing, that you really want to do after the equipment is de-energized and validated that it's, totally de-energized, go in with a vacuum cleaner and just make sure that the core and the coils are in fact free of particulate matter. Don't do just the front, but also remember to do the back. And that will add to your transformer longevity, because what we don't want to do is start having corona issues or particulate matter doing some tracking in the transformers. And because typically what happens is that's a death by 1,000 steps, okay? Once it starts to happen, it's very hard to make it stop. The other thing is transformers are warm, okay? One of their natural byproducts is heat. Depending on what the critter situation is in the building, this is where critters like to come in the wintertime, okay? So another good reason to keep, to keep an eye on this piece of equipment, because, doesn't matter if it's a tool, doesn't matter if it's a tail of a critter, doesn't matter if it's a whole critter, okay? Equipment doesn't like phase-to-phase faults, okay? So of all the equipment we're going to talk about today, this is the one that you really want to keep the cleanest, and this is the one that you want to look at the most. So, but the nice thing is this is also the simplest piece of equipment. So, it's kind of a win-win type thing. So, again, the big thing about this is 13.2 to 277 480. You've got fans. If we have that situation where it's the middle of summer, it's the 10th day of 100 degrees C, everybody in the building is running their air conditioner, the chillers are on full, you have a transformer here that nominally is designed to pull 1,500 kVA that can go up to 26.6. Now what that equates to in real live workable amps is, we can go from we can go from 1,800 nominal amps, so roughly 2,000 amps. We can go up to 3,200 amps. So you could almost double the capacity of the transformer with the fans running. So, that you've got some good overcapacity built into here. And the main circuit breaker is designed to accept, a higher amperage than it would normally go. So the nice thing is, on that 7th day, when it's 100 degrees, and everybody's running their air conditioner, even though you've asked them not to, and they say, I don't care, you have a piece of equipment that's going to be able to absorb that overcapacity. So just wanted to make you aware of that. Okay? So let's move down to after it stepped down to 480. Okay, so now we're down to the 480 volt part of the switchboard. The coming across here, instead of having cables, which we've talked about so far on the medium voltage, cables are coming into your main Pico compartment, cables are coming up to your load interrupter switch, cables are coming into the primary of your substation transformer. Cables are not connecting these two pieces of equipment. What we use is something called flex braid. And basically we do that because transformers also have a tendency to hum and vibrate. And so what that flex braid does is it's a way of eliminating passing on that vibration onto the rest of the equipment that's downstream. So you do have a sight glass in here, so you can take a look at the flex braid connections that are coming from the transformer onto the equipment. This is the main incoming section of your equipment. There's a couple of important pieces of equipment components I just want to talk about. The first one is your multifunction meter, which you have up here. As you can see, it's a little bit different looking than the one we saw on the medium voltage. This one is a little bit easier to read, and as you can see, it automatically cycles through the various parameters. So now it's looking at the phase-to-phase voltages. Now it's looking at the the amperage that it's pulling. So this is pulling about 2,000 amps right now. Okay, so when you look at this piece, of equipment, what's really nice about it is it will cycle through the various things. Here you can see the hertz. And there's little red indicators on the side here that tell you what the functions that it's doing, okay? So it'll say, hey, I'm now displaying you all 3 phases in amps. Hey, I'm now displaying you all 3 phases in volts. Hey, here's what the energy is. Hey, here's what the power is. So the nice thing about this is, if you just stand in front of the equipment and just wait a little bit, it will tell you everything that's going on with this piece of equipment, so you don't even have to press the buttons and things like that if you want to. Again, this is probably hooked up to the building automation system, and you're getting that information in. So the nice thing about this is every one of these substations on the main, you can tell what's going on from an electrical power utilization in this piece of equipment. How many amps am I pulling? How many volts am I pulling? The other nice thing is, especially when you're looking at the amps, the nice thing being able to see all 3 at once is, are my phases balanced? Okay, sometimes when you get into a residential application where you're going from 277/480 to 122/08, and you have tenants that are going to 122/40 because most of the time the load centers in the apartments are single phase. If the installing person didn't phase balance things properly, then you would have a meter here that you can look at instantly and say, hey, what's going on? But as you can see here, it's very, very well phase balanced. I mean, 28, 28, 28. So, good job on your installation. So that's the main multifunction meter. The next device down here is the surge protected device, or SPD. In the old days, we called them TVSS, transient voltage surge suppressors. This is in case you get any kind of surges on the line. This will dampen those down, so sensitive electronic equipment downstream won't be affected. Where this is really more practical from your guys' standpoint is you probably have some large chillers involved in this piece of in this building, and a lot of people don't talk about it, but switching transients from turning the contactors on and off on chillers is a main contributor to transient voltage. Everybody thinks, it's switching surges from the utility, or it's a lightning strike from the storm. Yes, that's true, but 75 to 90% of them are usually generated internally. And so the nice thing about this is, if you're getting those switching transients from your large chiller devices because of the contactors slapping in and out, this will help them to dampen that out. So if you do have any severe transients, not only will it capture it, but you also have on here a counter. So if you ever come up here and you see numbers on here, okay, then you'll know that you have experienced some transients. Quite frankly, it's really rare downtown that you see this. I'm just letting you know. I've only had one of these in my life where I've really gone to a place and have seen the counter actually off of 0, and that was down in Delaware, and there were some very unusual circumstances, and after the guy explained it to me, I went, oh well, it makes sense. It's doing its job, no problem. From a maintenance standpoint, the one thing you want to be careful of is if this alarm is activated, or if any of these lights are not red, not green. So if you see a red indicating light, that means something of a dramatic nature has happened, and this unit has intercepted that and shunted it, but it was of such a catastrophic nature that the unit itself became damaged. Now, that would really have to be something catastrophic. The unit itself, I think, is rated like 200,000 or something like that. I mean, it's a very high rated unit. So, I mean, again, you'd be talking something very severe for the unit to activate. But the main thing you want to do is, again, make sure it's in the on position like it is now, so the handle is vertical. And number two, just make sure that your lights are green. If either one of those conditions are bad, you know, double check everything on that. From there we go to the main breaker. This particular type of lineup is a main with some distribution section and then a tie over to the other piece of equipment. So this is what we call a double-ended unit substation. So just like the equipment we had downstairs, where I have one side of the equipment feeding one part of the building and the other side of the equipment feeding the other part of the building, this is set up the exact same way. The difference is this has a mechanical key interlock. So unlike downstairs where if you saw a loss of power from Pico and you were in the auto and the auto manual was in the auto position, it would automatically do the throw over. If for some reason, you needed to, do a single-ended situation up here, this would be a manual step, okay? You would have to take the key, you would have to open the breaker here, through the open. The key would then be released. You would walk over to the tie breaker, which looks just exactly like this. You would stick the key in there, rotate it, the key would then become captive, can't take it out, and then it would give you the ability to close the tie breaker, and then you would be single-ended the lineup from the good source. So in that particular case that I just walked through, let's say you needed to single-ended, so I would first open the breaker, I would rotate the key, it would be removed, this whole substation side would be dead, no power would be flowing through it. I would go over to my tie breaker, stick the key in there, rotate it, which would allow me to then close my breaker, and then what would happen is the other substation through the bus tie would feed everything up to here, okay? So all the power would come straight up until to the load side of this breaker, but from this side on, it would be dead, okay? And I would be feeding the line from the other side. The last thing I want to talk about in this piece of equipment is this device here. This is what we call a RELP switch, okay? And basically, again, we want to do everything in a de-energized situation. However, Philadelphia is under the 2020 National Electric Code. One of the things that's part of the National Electric Code is if you have a breaker over 1200 amp, you have to put in some sort of arc fault mitigating technology. The way that we do this is something called a RELP switch or a maintenance switch. What happens here is you have the ability by activating this switch to change the instantaneous performance of this breaker. So instead of this breaker being at like 10x, so this is a 2000 amp breaker on an instantaneous function, it would normally be set to trip at 20,000 amps. 10 times 2,000 would be 20,000. Well, one of the things that you can do to mitigate arc flash is to put in a lower set of values, typically somewhere around 1 or 1.5. So that way, instead of having to wait to 20,000 to trip, the breaker trips at 3,000. Okay, so again, that's something that the National Electric Code requires. Pennsylvania and the city of Philadelphia is on that National Electric Code, so that's why you have this switch. It's there to minimize arc flash in energized situations. We still prefer you not to do energized work, okay? But this is the way that the National Electric Code mandates it, and this is better than having the breaker set at 10x, okay? So, any questions about the main incoming section? So there you go into distribution breakers, okay? And these are large breakers that feed other pieces of equipment. Here you can see this is going to the automatic transfer switch. Again, this particular breaker is 1600 amp, so it has a RELP switch, okay? Here you have another breaker, and even though it's a very large spray breaker, it's only rated 800. So I don't have a run switch associated with it, okay? So these are going to very specific feeders, and they look like they're mostly automatic transfer switches, okay? This is going to a large power panel, and, you know, and section going on to those power panels right over there. Yeah, probably. The way you operate these breakers is, as you might think, these are what we call stored energy breakers. So the way that you operate them is, you can see there's a little handle here. So on smaller breakers, you have like a toggle, okay? You can throw that with mechanical energy. Because these breakers are so large, they have springs inside them, because you couldn't, you know, two small boys, a dog, and a lever wouldn't be able to throw this breaker, okay? So this is what we call the stored energy breaker. What you do is you use this handle to crank it down, and what it will do is, right now it says discharge, so this particular breaker, the springs are discharged. So what you would do is you would crank the handle down until it says charge, okay? You'll also hear a dirt, you know, like the springs are then charged, okay? That would give you the ability to then close the breaker if you wanted to at that time. So you can open and close the breaker through these push buttons, and you can also see, are the springs charged or discharged through these mechanical flags. So the nice thing about this is you do get a free reclose. So you can open, close, open, because we do that a lot of times for automatic throw over. But again, the important thing is are these springs charged or discharged? And the only reason I bring that up is you may have a situation at 2 in the morning where somebody is doing work on this automatic transfer switch, let's say. So they're going to push this breaker open, they're going to do their lockout tagout procedures, they're going to do their work on their automatic transfer switch, then they go away, and then, oh, you know, let's say, oh yeah, I forgot, you know, you got to do that. So then you come back here, and now you're trying to hit the close, and you're like, I don't understand. Why is it, I'm pushing the button, why isn't this breaker closing? Well, it's because the springs are discharged. So I have to crank the handle to get the springs to a charge. Is this one? Discharge, okay, yeah. So, yeah, it's actually,
You usually see them left charge.
we usually do see left charge, yeah. So, you know, again, you know, that's, you know, there's no harm in leaving the springs in the charge situation, but it's up to, I'm not telling anybody how to run their breakers here, okay? I'm just telling you there's nothing wrong with leaving the breakers closed in the charge position, okay? From a safety standpoint, I could see where, you know, it might be an advantage to leave them in the discharge position, mainly because these are draw-out circuit breakers, and even though there's an interlock, you know, it's personal preference, whatever you guys like is fine. Okay. Any questions on the feeder breakers associated with this? Okay. Let's go over to the tie breaker here. So this is the tie breaker. Unlike the equipment where we look downstairs, where the lineup was all in one big lineup, we could have done it this way up here, but usually architects don't like to have really big electrical rooms. So to save space, the idea was, well, rather than have one big lineup, why don't we split it into 2 smaller lineups, and then we can use, you know, and then we can connect the tie breaker from one piece of equipment to another. So that's what this is. This is the tie breaker. On the other side, it's an open section without a tie breaker. If you look up here, you'll notice a piece of busway. What this is a set of bus bars housed inside a mechanical enclosure, and rather than using cables to join the tie breaker to the other piece of equipment, we're using bus bars to do that same type of operation. The nice thing about this is it's a lot easier to install, and it's a lot more efficient than, you know, pulling like 15 sets of cables, and it's also lighter weight. So we see this very often on split substations. So this is the tie breaker. As you can see, there is no key in it. because this is a 2 out of 3 breaker scheme. So 2 of the breakers will always have a key in them, 1 of them will not. This is the normal operation. The tie doesn't have the key in it, but if you were going to single end, the tie would have a key in it, and one of the mains would not have a tie. From a maintenance standpoint, on the switchboard, just like all the other pieces of equipment, keep it clean, use vacuuming, exercise the breakers. We've already talked about how to charge. Just work it through once a year. Exercise the breakers. Breakers do not like to be left idle. Okay. The one thing you don't want to have happen is the breaker calls for a trip and it hasn't been exercised, and we have an issue. So we're trying to avoid that. You can see here is the busway that is connecting the 2 pieces of equipment. This busway is the same busway that is running throughout the building vertically to give power to each one of the floors. So you would have a large circuit breaker like this, and just like it has a piece of busway coming out here, but instead of going over to another piece of equipment, it would somehow go out the back probably and go down to service another floor, and it would probably say busway 1, or busway 1, 2, or something like that. The thing about busway is it's very good, it's very practical, it's all enclosed, it's got insulated bus. The only thing you really need to do from a maintenance standpoint when it comes to busway is, again, keep it clean, but most importantly, and this goes kind of the question that you had a little bit earlier, if there's one thing that you do want to check the torque values on, it's the bus joints. So everywhere where these pieces of bus are tied together, there is a bolt. What you want to do is check those bolts annually to make sure that they're tightened to the proper torque so that they don't work loose. So, any questions on the switchboard or the busway portion of the unit substation? Okay. So, that pretty much concludes our walkthrough of the equipment. Hopefully, this will serve you well. I want to thank you for purchasing ABB equipment. Thank you very much for doing that. And again, Jason and I are around. If you have any questions, feel free to give us a call. We like you to use our equipment, and we like you to keep using our equipment. Okay?
Thank you for your time.
Thank you, guys.
Okay.
Thank you. Thank you. Thank you. Thanks.